Hi everyone, Dr. Nat here. So we are doing second law of thermodynamics. Don't remember what part it is. Hopefully this is the last part. Alright, so we are going to talk about heat engines, refrigerators. Okay, let me just write that down. Heat engines, fridges or refrigerators, and also heat pumps. But we will start with heat engine first. Okay, so what is a heat engine? A heat engine is basically a device, right? A device that takes in heat energy. So it takes in heat energy, goes into the system, and in return, after it absorbs the heat energy, it will do some mechanical work, or it can be electrical as well. So work done by the system. Work done by the system. Okay, so it is losing some of this QH in the form of work. And what happens to the rest of the energy that does not get used up as work? It becomes QH, or the heat energy, becomes QC, or the heat energy that is expelled. You can imagine this as if you are eating food, right? So let me write that in the different color because this is just an analogy. So you take in food. You are the system. This is you, alright? So you take in food, and with that food, you get some energy to do some work. So you use that food to go for a jog. But not all of that food is converted into jogging, right? Some of that food has to become waste, or to put it more bluntly, it becomes poop or urine, right? So all of the food that you eat is not necessarily converted to work. Some of it becomes waste, and that waste, you expel the waste from your body because you don't need it. So this is your poop. Okay, I am sorry for the language. So you take in food, you do some work, or you jog using the energy that you got from the food, and some of that energy, you can't use all of the energy, so some of it becomes poop. Okay, so that is the analogy here. So don't write this in your exam. This is just an analogy. So heat energy is absorbed, right? So let's write that absorb. This guy expel. Okay, both of these are energy. So this is heat energy. This is also heat energy, but this one is absorbed. Remember, we learned in the previous parts that absorbing means positive, expelling means negative. You take out the heat energy from the system, and work that is done by the system should be in negative as well, right? Okay, but never mind. So let's talk about Q first. So where does the heat engine get QH from? So it gets it from a heat reservoir. So let's write that down. Heat reservoir. Okay, so it's a French word. That's why it's like that. So this is a cold reservoir. So the QC gets expelled to a cold reservoir. So as the name states, heat reservoir will have a higher temperature. Cold reservoir will have a lower temperature. Again, I'm going to repeat myself. So this system, this heat engine system, absorbs QH, absorbs heat energy from the heat reservoir, does some work. Okay, does some work. It can be either mechanical or electrical or anything really that you design it to be. And the system expels heat energy called QC to the cold reservoir. So all of this happens in cycles. What does that mean? It means that it keeps on repeating itself, repeats and repeats and repeats. So it starts from number 1, it absorbs the heat energy from the heat reservoir. The system does some work, so this is number 2, and then it expels heat energy to the reservoir of lower temperature. So this happens 1, 2, 3, 1, 2, 3, 1, 2, 3. So it happens in cycle. It keeps on repeating itself. And because number 1, number 2, number 3 happens in cycles, right? After 3, it goes back to 1, 1, 2, 3. 1, 2, 3. So we call these processes, 1, 2, 3 process, part of cyclic process. Cyclic process. Okay, because it happens in cycles. So based on this heat engine, we come up with the second, I didn't come up with it. So the second law of thermodynamics states that no heat engine operating in a cycle can absorb energy from a reservoir. So this is your QH, right? Can absorb energy from a reservoir and use it entirely for work. Use it entirely. What did I tell you? When we have some food, some of it becomes work, some of it becomes poop, right? The same case here. When we absorb a certain amount of QH, not all of the QH becomes work energy. Not all of it becomes work. Some of it becomes QC. So this is what the second law of thermodynamics states. Alright? So let's draw our schematic representation of a heat engine. So we start with hot reservoir, and this gives me my QH, right? And this is my system. Okay, and I will get QC into my cold reservoir. So let's make it a cloud. Okay, and in return I will get work by the system. Okay, so based on this, if I said I take in some QH, some of it becomes work, some of it becomes QC, which means that QH is really just W plus QC, assuming that we don't lose energy to anywhere else, right? So QH should be equal to work plus QC. So that means if I wanted to calculate for work, work is equal to QH minus QC. Okay, so because we are absorbing QH and we are expelling QC, that is why we have the negative sign here. However, some of you get confused with this, so this is why the modulus is put there. So QH in modulus, QH modulus minus QC modulus, so that there will be no issue of expelling or absorbing or whatever. So this is the equation that you should use. Work done by the system equals to QH absorbed from the hot reservoir minus the QC expelled to the cold reservoir. You don't have to take into account whether it is absorbed or whether it is expelled because of the modulus sign. Just use the minus sign here. Don't have to figure out whether it's absorbed or expelled for the signs. Okay, so if I have a heat engine, right? I have a device which is a heat engine. I wanted to know, okay, what is the efficiency of my heat engine? How much work can it do for me? So in that case, I need to calculate the work done that it can give me over the heat that it absorbs, right? So the efficiency of a heat engine, we label this as small e. Okay, so E is equal to the work done by the system over the QH that it absorbs. We already know that work is equal to QH minus QC, and QH is just QH. So this is your equation for efficiency of a heat engine. So the efficiency of a heat engine tells me the amount of work that the heat engine can do for me over the amount of heat energy that I need to supply to the heat engine. Or in simpler terms, efficiency of your body is the amount of jogging that you can do over the amount of food that you need to eat. Okay, so for an efficient human being, you only need a little bit amount of food to jog like 5 kilometers. But if this person is inefficient, it might need more food to do the same amount of jogging. So this is what efficiency means. It means, hey, how much output can you give me? hey, how much output can you give me if I give you this much input? So if I were to draw the operation of a heat engine in terms of a PV diagram, let's say it looks like this. It's just, let's say, okay. So this is number 1, so it goes from here to here. This is the point A, point B. This is number 2, process number 2. So it goes from point B to point C, and C to A is process number 3, and it goes back to process number 1. What is the work done? If we are looking at this PV diagram, what is the work done by this heat engine? How do I calculate for that? Previously, we talked about PV diagram and the curve, right? The curve associated with the PV diagram, and whatever that is underneath the curve, bounded by the x-axis, this is the work done. But now we have like 3 curves over here. What is the work done? The work done by the system is actually the area enclosed by the 3 curves. Okay, so again, I'm going to repeat myself. The work done by a heat engine is the area enclosed by the 3 curves. Why do we have 3 curves? Because we have 3 thermal processes in a heat engine. Whereas for this PV diagram, we only had 1 thermal process, which is why our work done is just the area under the curve bounded by the x-axis. So it's different. 1 curve here, 3 curves here. So this brings us to our next topic, which is the heat pump versus the heat engine. Now, in the heat engine, the heat energy went from a hot system, no, not from a hot system, went from a hot source to a cooler source. And we believe that this happens naturally. Let's say I have a hot object. This is like 100 degrees Celsius, and this is like maybe 20 degrees Celsius. The transfer of heat happens from the hot object to the cold object, and we know this is like a natural process. So it happens naturally, and in return we get the work done. Okay, just bear with me with this explanation for a while. So we know that hot to cold is a natural process. Now, for a heat pump, it goes from cold to hot, which is not a natural process. So let's write that down. So we have the hot reservoir, we have the system, we have the cold reservoir, but now we start from the cold reservoir, the cold source. So the cold source supplies QC, the heat energy, to the system, and the system expels QH to the hot source or the hot reservoir. And we know that transferring heat from a cool source to a hot source is not a natural process. We need to supply work to make this happen. So a heat pump takes in work, absorbs energy from the cold reservoir, and expels heat to the hot reservoir. Now, heat pumps can work in 2 modes, which is the cooling mode and the heating mode. So I attempted to draw a fridge. This is you, this is not me, this is you. This is the front part of the fridge, the inside of the fridge, and this is the back part of the fridge. Okay, so the back part of the fridge, let's assume is the heat pump. Okay, so this guy is the heat pump. It is part of the fridge. So the heat pump is part of the fridge, and the fridge is operating in cooling mode. Okay, so what happens here? Let's use a different color. So a heat pump takes in QC from the cold reservoir. Let me draw that differently. So this is a cold source because this is a heat fridge, right? The heat pump takes in the QC from the cold source. What happens to the QC? It goes out of the fridge in the form of heat, QH. And this is the environment, which is obviously hotter than the fridge. So this guy is actually the hot reservoir. And where does the work done? Where is the work supplied? The work is your electricity that you are paying to keep this fridge running. So the electricity that you pay to run your fridge is you supplying work to the fridge. Okay, again, I'm going to repeat myself. So the heat pump takes QC from the cold source, which is your fridge, and it expels the QC from the fridge and lets it out in the form of QH. The QH is expelled into the environment where the temperature is much hotter than the fridge. So this becomes our hot reservoir, and the fridge is our cold source or our cold reservoir. And the work supplied to the heat pump is actually the electricity that you pay for to run your fridge. Okay, so this is the cooling mode. What about heat when it is operating in heat mode? So what heats stuff up? A heater, right? A heater. So let's draw that. So how does a heater work in heating mode? So a heater is used in places where it's cold, right? Where you have winter. So imagine the cold source is outside because you want to heat up your home. Outside it's freezing, it's snowing. Okay, so outside it's snowing, so this is your cold source. So QC is absorbed by the heat pump. You pay the electricity to run this heat pump or this heater, and this is your work that you supply to the heat pump. And the heat pump expels QH to your house or your hot reservoir, because obviously your house is going to be warmer than the outside environment where it is snowing. And obviously you don't want to stay outside because it's freezing, so you stay inside your house. So this is your house, and this is you flying. Don't know why. Okay? And because your heat pump operates in two modes, cooling and heating, your COP depends on the mode that it runs. So if you are using a fridge, the COP would be how much heat energy that can be expelled from the fridge. So that is a QC, right? What is the QC over the electricity bill that you are paying? So this is for cooling, because you are interested to know how much heat energy can you expel from the fridge so that it becomes cool. This is cooling mode. You are interested in QC. And the COP for a heater, you are interested to know how much heat energy can this heater give me over the amount of electricity that I pay for, right? So you are interested to know what is the heat energy supplied by the heater over the amount of electricity that you are giving. So this is in heating mode. So it is dependent on what you want actually. And because both of this, let me write that in a different color, because QC is energy, it's in joules, work is also in joules, so this cancels out, so COP does not have any units. Okay, and the larger the COP, the better the performance. Which is true, because if you want your heater to expel a lot of QH over a little amount of electricity that you pay for, then your heater is very, very efficient, or the performance is spectacular. Okay, so let's do a little recap before we start with Carnot engine. So we have learned about heat engine. A heat engine absorbs QH, takes in QH into a system, this is your system, gets expel QC into the cold reservoir, takes this guy from the hot reservoir, and in return it gives us work. This is a heat engine. And the second law of thermodynamics says that a heat engine that absorbs QH will not be able to fully convert this to QC. Will not be able to fully convert this to work done, because some of the energy needs to be expelled as QC. So that is our second law of thermodynamics. Okay, so a Carnot engine is also a heat engine. However, it is an ideal case for an engine. An ideal engine, which means that its efficiency of a Carnot engine must be greater than the efficiency of a real engine. The efficiency for an ideal engine should obviously be better than the efficiency of a real engine, because real engine works in real life scenarios and it is a not ideal case. So efficiency Carnot engine must be greater. Okay, but the operation is still engine lah. Okay, so to draw the PV diagram of a Carnot engine, we first need to understand that a Carnot engine can work in reverse. It is a reversible process. We learned before that for real engines, we go from 1 to 3, 1 to 3, it happens in cycle. I did not mention about reversible because it can't be reversed. But for a Carnot engine, because everything is happening in ideal situation, we assume that it can be reversed. Okay? And to draw the PV diagram, it looks like this. Ooh, that's funky. Okay, so this is my V, this is my P. Let's use a different color. So we start with an isothermal process from A to B. Isothermal, if you guys still remember, isothermal means the temperature is constant. This means that the change in temperature is 0. You supply heat in the form of QH, and because it is expanding, right? It is expanding from this point to this point. You have learned that when a piston expands, it is doing positive work on the environment. So this process gives us positive work to the environment or negative work done on the system. Okay, but we are talking about the environment, so it is positive work. So this is your first process. The second one is adiabatic expansion. So B to C is adiabatic. And if you guys still remember, adiabatic means Q is equal to 0. And because it is still expanding, we are still doing positive work to the environment because it is still expanding. And then C to D. How should I draw this? C to D. Boleh lah. C to D. So this point is D. This is an isothermal compression. We have learned in the previous parts that for a gas to be compressed, the environment has to do work on the system, right? So if the environment has to do work on the system, which means that now we have negative work by the environment. And in return, we get QC. Previously, we got in QH. Now we get QC from this isothermal process. And then the final process is D to A, which is an adiabatic process. Okay, adiabatic process. Adiabatic process, this is adiabatic compression. We still need to supply work from the environment to compress the system. And at this point, this is an adiabatic process, so Q equals to 0. Okay, so what did we get from this cycle? We got QH into A and B. From A to B, we got QH, and then from C to D, right? From C to D, we expelled QC. So here, for the Carnot engine, the work done by the Carnot engine, it can be written like this. Work done by the Carnot engine is equal to QH minus QC. This is the net work done by the Carnot engine. Okay, modulus that guy. So this is the first equation that you need to know for a Carnot engine. And for a Carnot engine, the relationship between thermal energy and absolute temperatures is as the following. So QH over QC is equal to, let's modulus that, is equal to T hot over TC, where TH is in Kelvin and TC is also in Kelvin. And you're asking me, Doctor, macam mana boleh joules equal to Kelvin, right? Okay, I hear you. So this is the relationship, right? The relationship is between this ratio and this ratio. This is joules over joules, which cancels out. This is Kelvin over Kelvin, which cancels out. So this is how they can be equal. However, if we were to say, okay, QH is equal to TH, this is wrong because this is not a ratio. This equation has to be in ratio form for it to be valid. If I say 1500 joules is equal to 500 K, it's wrong because joules can't be K. So use this relationship, okay? Do not use this gut, it's wrong, okay? So this was your first equation. Let's use a different color for that. Blue. First equation, second equation, and your efficiency, which is from the heat engine part, is work done over QH. And it is the same for a Carnot engine. Work done here is QH over QC. Oops, QC, modulus that, over QH. And there's another equation for the Carnot engine. You can use this, it's correct. The efficiency can also be written as TH minus TC over TH. And because TH over TH is 1, it's equal to 1 minus TC over TH. So this equation is just for the Carnot engine. Just for the Carnot engine. Okay, so let's do a little recap. We know that the ones in purple can be used for real and for Carnot. This guy is for real and also Carnot. This only applies for Carnot. And this guy. Okay? So hope that helps. See ya.